Here's a run through the key for the test. So this first one here, it's a pressure vessel. You want to find the hoop stress, and then the axial stress, which is half of the hoop, so 448 megapascals and 224. The hoop tries to tear the tank in half along the long axis, so the hoop acts in the x direction, and the axial tries to tear the ends off the tank, so there's the axial. The maximum tensile stress is just the hoop stress, so it's 448. The maximum shear stress in the tank wall is based in a biaxial analysis, so I show the element right there that you'd work with. And then what you do is you use this formula to find tau max. Now sigma min in this case will be sigma z, which you can consider to either be 0, or you could even take it a little bit further and consider the stress in the z direction, which is normal to that plate that makes up the tank, as being the internal pressure, which is 8,400. It's negative, so you'll have 448,000 minus a negative 8,400 over 2. So you could get either 228,000 or a little more precisely 228,200, I think. So so it either be, 224,000 or 228,200, one or the other. Okay. All right, the next one here is Hooke's law. So find the strain in the x direction, 1 over e sigma x minus nu sigma y. You'll get 0.0558. 1 plus that times the original x length of 7 will get you the final length in the x direction, 7.39. To get the change in angle ABC, you find the shear strain, gamma xy, which is tau over g, 0.04 radians. That's a positive answer, so what you get out of that is a lessening angle for angle ABC. So the angle ABC starts off as a right angle, 90 degrees, which is pi over 2 radians. Subtract off the 0.04 shear strain, and then convert to degrees, you get 87.71 degrees. Okay, the next one here is biaxial strain. What you're doing there is you want to find epsilon x, epsilon y, and gamma xy. There they are. So in the x direction, it's getting longer by 8,200 times 10 to the minus 6. In the y direction, it's getting shorter by 2,100 times 10 to the minus 6. And the angle there is getting greater, which means it's a negative shear strain of negative 4,000. You then just plug it into the biaxial strain equations. Now in both cases, you're going to use 33 degrees, both for the normal strain, which will get you 3,318, and the shear strain, which will get you negative 11,037, both of those times 10 to the minus 6. Okay, this next one here, are there two-step problems there? You've got epsilon x, epsilon y, gamma xy. You're told that half of the shear strain acts on either line, so half the shear strain is 0.06. So to get the deltas, you take the strains times the original lengths. So for delta x, it's the negative 0.015 times 8 centimeters, it's negative 1.2 centimeters. For the deformation perpendicular to those lines there, you would take half of the shear strain, which is 0.06 times the 8, so that's 0.48 centimeters. For delta y then, it's 0.1 times 8 centimeters, 0.8. So we're using these values here to figure out the new positions of points A and C. So for instance, C here will move inward by 1.2 centimeters, so each one of these hatch marks, the distance between them is a centimeter. So that'll move in, and then it'll kick out to make the angle smaller because of the positive shear strain. That'll kick out 0.48 centimeters. Similarly, in the y direction, we're lengthening by 0.8 centimeters, and we kick out to lessen the angle by 0.48 centimeters. So there's the final locations of A and C. Okay, the one after that, you find the moments of inertia, pi over 2 R4 for the first one, and pi over 2 outer radius to the 4 minus inner radius to the 4 for the second. Okay, this next one here, what we're doing is we're going to take the horsepower, convert it into foot-pounds per second by multiplying it by 550 foot-pounds per second per horsepower. Take the revolutions per minute and convert that into radians per second, 23.6. Divide the power by the angular speed to get 934 foot-pounds, which is 11,204 pound-inches there. That's the power. Now the torsion then, I'm sorry, that's not the power, that's the torsion, okay? Because we've taken the power and divided it by omega, and that gets us the torsion. So the formula for that is the torsion times the angular speed is the power. So if you want the torsion, you can take the power over the angular speed. There we go. So that's what we're doing right there. And that gets us the torsion, 11,204 pound-inches. Okay, now what torsion is the moment about a shaft. So you want the distance. You have the weight already. That's what you want to find. You want to find how far it is from the center of the shaft. That's half the pulley diameter, which would be the radius. That's 7.5 inches. So the 11,204 is 7.5 inches times the weight. So the weight is 1,494 pounds. Okay, the next one there, we've got the moment of inertia. You already calculated. It's 4.02 times 10 to the minus 6. You've got tau max and sigma max are TR over I. So you just plug those things in and you get 3.58 megapascals. Now, to find the normal stress on that line, you need the proper angle. You can either use negative 18 degrees or 162. Also, based on this torsion, you have a shear there that is negative on the x-plane there. So tau xy is actually negative 3.58. So you got negative 3.58 times the sine of either 324 or negative 36. So that'll get you a positive 2.10 megapascals. Okay, the last one is finding the twist angle. The formula there is TL over I G. You want to find the torsions for each section of the shaft. Find the reactive torsion here first. It's 180. Going like that, draw up a free body diagram. You can find the internal torsion anywhere between A and B is a negative 180. And then you can find the internal torsion anywhere between B and C is a positive 120. So there you go. And then you just take TL of each segment there, divide it by I and divide it by G, and you'll get the twist of each segment. Okay, so the first one of B with respect to A is negative 0.04776, and the next one going from B to C is positive 0.02123. Add them together, you get a negative 0.02653 radians, which is negative 1.52 degrees. So that's how C twists with respect to A.